Go. So I'm David Simmons. I'm from InfluxData. Ian asked me how long I'd been there. Have you been there long? And I was like, well, it's only been since August, but it seems like a really long time. And I do have a demo, but I'll do the full demo in the booth later this week. I just brought some flashing lights and stuff up here because that always makes for things to be more fun, right? And I'm going to talk about data collection, but pushing data collection to the edge. You know, data collection can happen kind of almost anywhere in your architecture, and there's all sorts of questions about where you collect your data, right? Do you want to do distributed data collection? Do you want to centralize your data collection? And there's all sorts of trade-offs between both of those things, right? For centralized data collection, are you able to afford the network connection, right? I have been doing IoT for a really long time, and I always boil IoT down to the most important part of almost any IoT calculation is power, right? And it's the power requirements of the least powerful device. So it's typically the very edge sensor power requirements that are going to drive almost everything in the deployment. Because at some point, you've got to calculate how long is that battery going to last, how much power is on it, and the most expensive part of almost any sensor reading and data collection is the network, right? Transmitting the data and reading back from the network. So if you're doing centralized data collection, you're going to have a reliable network, a fast network, low latency, and you're going to have a fair amount of power on the end device so that you can make sure that your data is transmitted all the way from the edge device back up to your back-end system, right? If you're doing sort of edge data collection, then you can have much less reliable data connections between your edge device and your back-end system, but your edge device has to be able to collect and process and handle all of that data locally when the network is offline, right? And yeah, I've got to ask yourself questions about, does all my data need to be in the cloud, right? Do I really need all of that data at the back-end system? How much do I need? And that's based on how is that data going to be used? Who's going to be accessing that data? What are they going to do with it? Are they going to be making critical, machine learning decisions based on it? Do things have to happen based on that data in real time, right? If things have to happen on that data based in real time, then you better have a really fast, really reliable, low latency, high speed network from your sensor to the back end and back every time, or things are going to explode, right? I was speaking to a very large company that builds things like oil rigs not long ago, and they were really worried about this problem because they have to have the decision making as close to the sensor as possible. Because if the network connection from the oil rig in the Gulf of Mexico, if the data connection to the back end isn't reliable and that valve doesn't get opened like that, really bad things happen. Like oil rigs explode, and we've seen what happens there. So it's all about making decisions about where those things have to happen and what is your network reliability, and again, what's the power on the device? Does it have enough power to do these sort of long distance network connections, or do you want to have sort of shorter distance to a local device and deal with it there? So if you're going to collect it in the cloud, basically all of your data is flowing to one central point, right? Whether that's Azure IoT or AWS or Google Cloud or your own cloud or your own data center, all your data is flowing back there. And all decisions are made there, all data analysis is done there, and then any results have to flow back, right? So you need a high availability, low latency network in order to deal with that. And if you don't have one of those, or one of those is too expensive, then that's probably not going to work for your IoT deployment. And one of the things you get from that, though, is analysis and visualizations from anywhere, right? Because all your data is in one place, so anybody that with the credentials can connect to that data source and have access to all the data. So that's a great thing about having everything sort of one source of truth in your data collection, is that it's all in one place. Anybody can connect to it, anybody can see it, anybody can analyze it, at least as long as you have credentials and you're putting some sort of security around it, which I'm just assuming at this point. The alternative, of course, is to collect it at the edge. And there are lots of people that have lots of different opinions about what the edge is. We have been having a discussion with some other folks that I know about what is the edge. And some of them actually think that the edge is things like, the Azure IoT is the edge. And yeah, that's an edge. But again, if you don't have a high availability, low latency network from your sensors to the cloud, that's not really a reliable edge. And based on those power calculations and the network calculations, you may or may not have access to your data. So I look at the edge as close to the sensor as possible, sort of first hop from the sensor. And that's kind of what I've got up here. So I've got a temperature, humidity, and an atmospheric pressure sensor up here. And I've got a CO2 sensor up here. And I've got an edge collection device that you guys can play with later, and it is collecting all the data from these devices. So this is what I consider an edge collection device, right? It is one hop from the sensor. So I know that if this thing is not getting data from one of the sensors, either the network connection between this device and the sensor is dead or the sensor is dead, right? I don't have to wonder, is it someplace in the long haul between sensor and cloud, right? Is it an AT&T backbone problem? Is it an Azure cloud problem? I don't know. If I'm not getting data here and it's one hop from the sensor, I know where the problem is, right? So if I have unreliable backhaul networks, then collecting as close to the edge as possible is key. And it gives me the ability to do local data processing and analysis. So I'm actually able to, if I'm collecting my data here and I'm using this as a data collection platform, I'm actually able to do a lot of the analysis and response to sensor events locally, right? So I look at this device as something that, goes sort of on a shop floor or if you're doing a smart building, on a floor of the building, right? And the local maintenance guy has this dashboard and can see what's going on with all the sensors and the things that he's responsible for. And it takes care of handling events and data analysis for that local area, because that's the data that's important for that area and it needs to be processed and handled locally. And in fact, this glowing ping pong ball is not just a cute glowing ping pong ball. If I blow into the CO2 sensor, there's about a 15 or 20 second latency, but as the reading goes up, the color on the ping pong ball will change. Because this device, there it goes, I managed to redline it in 2 blows. This device is actually collecting the data, and it's analyzing the data, and it's responding to the data with right now I have not set up a connection back to my cloud instance. So this is all handling locally, right? I'm able to deal with all of my collection and response locally here where it makes the most sense, right? So if I'm on an oil platform, my oil platform's not going to explode because I'm able to deal with it locally no matter what my backhaul network looks like or the condition of it. So this is the distributed data collection model, right? I can have these things, one on every floor of my building, and each one handles each floor. or I have one on every oil rig, and each one is independent and can handle all the data from that local environment, right? And then I can feed those back to a back-end system. So ultimately, if this thing is connected to an internet connection, what it does is it downsamples its data and sends it to a back-end system, right? Because the guy who's in charge of all the oil rigs doesn't necessarily care about the pressure readings from every valve on a millisecond by millisecond basis, right? He's really concerned with what's the overall trend of the data and what are the sort of out-of-band anomalies. And so I can downsample that, and I can send that to a back-end system, and I can aggregate all of that in the back end where that's important, but still leave the local second-by-second decision-making. See, my CO2 concentration's gone down, and my light's back to blue. So it distributes the data collection load, but it also lowers the load on the wide area network, right? I'm not sending 100,000 sensor readings per second back to the, over my expensive network connection. I'm sending a downsampled version of that data. I'm doing, say a running 2-minute average, and I'm sending those 2-minute averages upstream. And I can store those until the upstream network connection comes online, and then I can dump those all out to the back-end cloud system. And when the network's online, and when the network's not online, I'm still not worried about things catching fire, right? And so the term that I've been using for this is really a data layer across my IoT deployment. I have a data layer that goes from the sensor devices to the edge network collection devices and all the way to the back end. And it doesn't really matter where that data is anywhere in that layer. It can still be handled appropriately at any place along that path. So I can collect it at the edge at as close to where it's generated as possible. And I can take action on it and display it and do analysis on it there. And I can either downsample it or send the raw data back to a back-end system where it can be further analyzed. It can be sent into machine learning programs and handled in aggregate. So I can aggregate all of my local edge collection devices to a central back end where it makes more sense to do larger analysis of all of the data coming from all of my sensors as opposed to just handling the local stuff, right? And I can do this on a network available basis. So that lowers my network costs, it lowers my deployment costs, and it's more fault tolerant because I don't have to worry that my internet connection is always up and always available and always fast. So I lay this out in what I call sort of a rational IoT architecture. I've got a bunch of sensors, and they can be connected however, Modbus, Wi-Fi, Bluetooth. One of these sensors is Bluetooth, one of these is Wi-Fi. I have a couple of LoRa sensors as well that I hook up to this demo, so I don't really care what that is. And I connect that to an edge device, which may or may not be connected to a back-end cloud, and that's sort of my system of record, right? Ultimate system of record is this back-end system, and I can do all of my analysis and dashboards and things like that at the back end. And so I've been talking this whole time, for 15 minutes now, and I haven't even mentioned InfluxData, which is kind of why I'm here. So my point in doing this whole thing, this was an exercise that I just undertook as part of my job to see what I could do with the InfluxData platform. How many people know about InfluxDB? Okay, so some hands. How many people know about InfluxData? Right, so InfluxData is the company behind InfluxDB. And we actually have a larger stack of data collection and analysis and storage products. They're all open source. And you're wondering why I'm here at Eclipse IoT. Well, we're part of the Eclipse Foundation, and I have been trying to push this ball uphill for the last sort of 7 months of trying to get us to move all of our open source stuff under the Eclipse IoT umbrella. It's currently a losing battle, so if anybody wants to start lobbying for that on my behalf, I'm happy to have the help. So we have this thing called the tick stack, and that's Telegraph is our data collection engine. And you can run Telegraph. I'm running Telegraph on this edge device. You can run Telegraph on the cloud. You can run Telegraph on pretty much anything. In fact, we have a customer that when any new machine joins their network now, they have about 165,000 devices on their network. And when any new machine joins their network, it comes with Telegraph on it, so that as soon as it comes up, it begins collecting data and logging data and sending it to an instance of InfluxDB, right? Every time I mention a number of plugins, it's wrong because we're adding more all the time. We have, I think, about 180 plugins right now for data collection, both input and output. MQTT, AMQP, I mean, you name it, there's a collection protocol for it for Telegraph. And it's a really high performance, open source, input and output source for data. And again, you can run that at pretty much any point in the stack. InfluxDB is the data storage engine. That's our purpose-built time series data storage engine. And I'm actually running that on this device as well. So I'm able to store my data locally on this device. And I can run it in the cloud, and I can store my data in both places. And I can downsample my data from one and store it in another, however I want to build that. So it's fairly small, it's fairly fast, and I can deploy it kind of anywhere across the architecture. Capacitor is our sort of co-processing engine. So if I set up Capacitor and Telegraph is sending data to my InfluxDB engine, it is at the same time sending that information to Capacitor. And Capacitor is what's handling the alerts for this little ping pong ball, right? It's constantly monitoring the incoming data, and it's keeping track of what the last values were over about a 10-second window, and any change in that data that is greater than about 50 parts per million in that 10-second data window generates an alert. And it actually writes a value to the Mosquito MQTT broker, which this ping pong ball is listening to, and it changes its color. Right? So again, I can run the capacitor analysis and response engine anywhere along the architecture. And I'm also running that locally on this device. And the last part of it is chronograph, and I should have put it in a different order because we call it the tick stack, T-I-C-K, and I put it up here as T-I-K-C, so that's my bad. I'll have to change that for the next set of slides. And that gives us our dashboards. And you probably can't see it from up here, but I've got a dashboard here with a bunch of charts and dials and graphs of the incoming data in real time, so that I can visualize my data in real time on a dashboard, and I can see what's going on with my sensor data as it's coming in. Right? And I can run those dashboards, again, at the edge. On this device, I'm running those dashboards at the edge, and I can run those dashboards in my back end, so that different people who need access to different visualizations of different parts of the data can get the visualizations of the data that they need. And I can build those dashboards pretty quickly in point and click and add components to the dashboard and change how the data is visualized depending on who needs to see it and where they are. So how does InfluxData help with this overall architecture, this data layer for the IoT? And I've gone over most of it, but it's really efficient data collection. So I love to hammer on MongoDB. How many people have used MongoDB for IoT deployment? Great, don't do that anymore. So we had an independent group of people go out and run a benchmark of data ingestion and query speeds against a whole bunch of stuff like Cassandra and MongoDB and Elasticsearch, a bunch of stuff like that. InfluxDB was ingesting about 1.4 million values per second. On the exact same hardware deployment, MongoDB was able to ingest about 24,000 values per second. So don't do that anymore, okay? That same data set, our storage, we're very efficient in storage, and our storage was about 154 megabytes. MongoDB storing the same data set was over 16 gigabytes. Okay, data storage isn't free. Network transmission of data isn't free. So you got to look at all of that when you're doing an IoT deployment. And if you're doing a small proof of concept, you may only need 24,000 values per second. But as soon as you start ramping that up, it's not going to scale. And you need something that's going to scale for not just the storage, but for the ingestion rates. Because that's going to be an ingestion rate for your data that is going to be sustained, right? Yeah, it may peak, but you're going to have a sustained data rate, and that's not a sustained data rate for a day or an hour or a week. That's going to be a sustained data rate for the life of the deployment, right? So being able to ingest, analyze, and query all of that data in real time in a high-performance way is really important to the success of an IoT project. And I believe it was last fall at a conference I was at, somebody presented the results of a study that over 70% of IoT deployments fail. And most of them fail because they didn't scale from the proof of concept stage up through an actual deployment. Right? I can do a proof of concept, it runs great, and I start rolling that out, and the thing falls over because it didn't scale. Ease of deployment. One of the things that we actually, that time to awesome phrase, our CTO and co-founder made us trademark that because he's really serious about that, making it really easy to deploy. If you're putting it on a Linux-based gateway device, I think my video for how long it takes to deploy to Linux was 3.5 minutes. To deploy the entire stack to a Linux machine and have a dashboard up and running in 3.5 minutes. It's a little less on a Mac. If you're running Windows, I'm sorry, we really can't help you much. And again, dashboards for visualization. You can build those dashboards anywhere along the data layer, and you can visualize your data in ways that make sense to your users for where they are and what data they need to see. So dashboards everywhere. This is a version of the dashboard that's running here, right? I've got a gauge that shows me my CO2 count right now in parts per million. Then I've got a running graph of it over time so I can see the change over time, but I have a dial graph that shows me where it is right now, right? I've got a light sensor value and a temperature. And then again, I've got a graph that shows that over time. And I've also got, on this one, I've got a CPU and a disk, and I have the wrong disk values on that graph. I should change this. But the CPU, you'll notice, is less than 20%. So it's running all this stuff for data collection, data analysis. It's running alerts. It's running dashboards. And it's downsampling the data, and it's using less than 20% of the CPU on this little embedded Pine 64, ARM embedded board. Same thing for a Raspberry Pi. The disk used, actually, if you follow the disk use, it seems to keep going up, but it's really only using about 15% of the disk, and it goes up to about 15%, and then we do a data compaction, it drops down below 10%, right? Now, this thing I built using a 64 gig micro SD card, and I'm including Linux and the entire stack and the data, I'm using less than 15% of my storage. So I can run this thing at the edge for a really long time and collect a lot of data before I have to worry about running out of space. One of the other nice things that I did not talk about in this is on each one of these databases that I'm collecting this data on, I can set data retention policies. So I can say, I want to keep all this data for 30 days. And any data that's older than 30 days, it automatically just drops off the end and goes away. So I can ensure that I don't run out of storage space by having data retention policies that make sense for how much storage I have on my device. And I can time out my data. And I can take that data and I can downsample that data and restore it someplace else before it times out, so I have an overall trend of the data, but I don't need the millisecond or microsecond or nanosecond level data forever, right? Because that really doesn't make sense. And so I kind of end up with, IoT data is time series data. If you want a definition of time series data, it's pretty much IoT data. It's a sensor reading at time, right? That's time series data. And yes, you can use a SQL database to store it in. You can use MongoDB to store it in. Don't do that. But you really should use the tool that's right for the job. So use a database that's built for the data that you're using, right? Now, a lot of IoT deployments, you're going to want to have metadata about your sensors and about other stuff. And you're not going to store that in InfluxDB, because that's not what we're for. You can store that in Mongo or MySQL or Postgres or wherever you want to store that. But the time series data makes sense to put in a time series database. Yes, you can pound a nail with a screwdriver, but it's going to be really hard and not an enjoyable experience, right? So use the right tool for the right job. Use the right database for the data that you're trying to store. I'm sort of repeat this all the time, that IoT data must be timely, accurate, and actionable. And the actionable is key. If you're not actually taking action on the data you're collecting, why are you collecting it? If you're not doing anything with it, why are you collecting it? If you're just collecting it so you can store it, then you can just have a random number generator that stores random numbers, and you can use just as much disk space and get just as much value out of it, right? Because if you're not doing something, you're not basing any decisions and taking action on the data you're collecting, there's really no point in collecting it. And historical data makes a lot of, you can use historical data for a lot of decisions. But for the most part, decisions are based on immediate incoming data, right? If I'm only going back and looking at my data that's a month old, well, yeah, I'll know that my oil rig is going to catch fire tomorrow, but I already know that a month later because it caught fire a month ago, right? So I need to be looking at my data now and taking action on the data that's happening now. And I can go back and do historical analysis on older data, but that's usually not what I take immediate action on, right? And IoT deployments are struggling to find efficient, scalable data platforms for doing this, right? Something that will work in the proof of concept and scale up to an IoT level deployment. Because IoT level deployments are different in scale than almost anything else, right? The numbers that people are always throwing around of 20 billion devices by 2020 and 50 billion by 2025, those numbers are really important if you're a device manufacturer, right? That's great for you. If you manufacture devices, the number of devices connected to the internet is really important to you. But what's really, really important is the amount of data that each one of those devices is going to generate. Because if you're connecting devices to the Internet of Things devices, chances are it's because you are interested in the data that they're going to generate. And so the amount of data that they generate is way more important than the number of devices. And typically a single device will generate multiple data streams, or at least multiple data values. So 20 billion devices will probably generate 40, 60, 100 billion data streams, values. And that's what really matters, is not the number of devices, but the amount of data that they're going to be sending at you. And they will be sending a lot. And so that's this is my only salesy thing, and I have to do it because the sales guys yell at me if I don't. We're kind of the only platform that meets all of that, that is scalable from data ingestion to action and can be deployed any place across the entire architecture. And one of the really nice things about it is it's the same code base. It's the same stuff. I am running the exact same code here that we're running in our Influx Enterprise Cloud instance that we sell to customers. It's the same code. It's just compiled for a different architecture. But it's the same code. So there's a real low barrier to entry, and it's cheaper to maintain because you're not having different code bases and different, well, I've got this data collector, then I've got this data collector, I've got this data collector, right? I've got a single code base across everything, and it runs everywhere, and it does the same data collection and data forwarding, and I'm done, right?
Can you repeat the question?
The question is there any limitation on the number of devices at the edge? Of course, because the laws of physics apply, right? So, and that's just a scaling factor of what the hardware that I'm deploying at the edge as my edge data collection device can handle, right? Now, this one is running a LoRa network. It's got a Bluetooth and a Wi-Fi, and actually deep in there is a Z-Wave network connection, right? So I can handle devices on any of those things. And I'm, when I've got the full demo running, I've got 5 or 6 sensors and about a dozen data values coming in, and I'm using less than 10% of the CPU. So you can scale that. And mine are sending anywhere from once a second to the CO2 monitor falls over if you ask it for data more than every 2 seconds. So, and it tends to fall on 2-second boundary, so I have it set at a value of about 3.5 seconds, somewhere in there, to stop it from killing itself. For some reason, the CO2 sensor kills itself if you ask for data too quickly. Yes?
David, really thank you. This is a great presentation, super clever. And it raises a great question. So lately I was looking at some data, and the data produced by devices in the entire history of IT computing, the large chunk has been done in the last 2 years, right? Mm-hmm. So you're talking about 2012, billions of devices, and it's actually a pretty good marketing pitch, right, for who actually manufactures those devices.
Right.
But the local processing would be a necessity, absolutely. No one, few industries, I know few people actually that are thinking about how we can save the amount of data we store in the cloud with local processing. And we have to develop stronger and stronger solution on the edge device, on the embedded side, in order to be, like when you don't have to care about storage, you probably don't think about it, but we will very soon. So yours was a really good point, absolutely.
Thank you. Yeah, and we should care about storage because storage costs money. You pay on Amazon or Azure, you pay for the data you store. So you want to make sure that the data you're storing is valuable and that you're not just storing data because you can, right? And that's where these retention policies and the ability to downsample data, and the more you downsample data, people think you're going to lose accuracy. Well, you are going to lose the granularity, but depending on how you do the downsampling, you're still going to maintain the overall trend, and so we can show you downsampling strategies where the data curve remains exactly the same, whether you're doing millisecond level or 5-minute averages, right? And so as you move farther away from real time, you downsample that data so you can store less, but you can still maintain the overall, the value of the data.
So we have a coffee break coming, so let's just take one more question.
Okay, thank you. Great presentations. Thank you for that.
Thank you.
My question is, when you connect all these sensors you showed in the rational block diagram, it's a very nice block diagram you put in. So the question is, all these sensors have got its own protocols, right? You just got the I2C or UART or the GPI, It is coming through the Wi-Fi, but can you talk about what protocol you use to connect all these sensors to your edge devices?
Yep. So I didn't want to just use one protocol, right? Because one protocol isn't real world. In the real world, I'm going to have a Wi-Fi device. I'm going to have a Bluetooth device. I'm going to have some LoRa sensor that's way out there, on the edge of my property, whatever, right? And so that's kind of why I built this the way I built it. So the Wi-Fi sensor is actually sending data directly to Telegraph using Telegraph's what's called line protocol, right? It's actually sending it in an HTTP packet to the Telegraph collector. The Bluetooth is connecting to this device over Bluetooth, and I wrote a small Go program to open the Bluetooth connection and read that data, and then again put it out over what amounts to a serial connection to Telegraph, right? So I'm using capacitor to do its output to an MQTT broker. I can just as well use an MQTT broker for my input. In fact, I was in Italy last week, and the workshop I was presenting at was using the Things network for all of their data collection. And so I said, well, we can get all this data into InfluxDB really easily. And they said, how easily? And it took about 5 minutes and maybe 10 lines of configuration in the Telegraph configuration file. And suddenly all of their sensor data from all of the students in this workshop was being sucked into InfluxDB. All I had to do was point it with the right credentials to the right MQTT broker, and all of the data came flying in, right? So there's a whole bunch of different ways, and you can pretty easily write your own plugins for Telegraph. And so when I first started at the company, I'd never written any Go, and it took me about 2 weeks to write my first plugin for Telegraph. The last one I wrote, which is to keep track of the battery health in this device, because this is battery operated as well as plug-in operated. The battery plug-in to monitor the internal battery took me a couple of hours. And that's just because I suck at Go. But it's fairly easy, right? One of the things that I had to do in building this was, it matters with a wireless device on the edge. What's the health of the wireless connection, right? Because I've got a Wi-Fi connection here to the back end, and I've got a Wi-Fi connection from here to the sensor. And so I've got to know, if I'm not receiving data from that Wi-Fi sensor, is it because the sensor died, or is it because the Wi-Fi network died? And so I wrote a plugin for Telegraph to monitor the Wi-Fi signal on a Linux box, and that took me about a day. And again, that's because I suck at Go. It's not because it's hard. And those two plugins, the battery monitor and the Wi-Fi monitor, will actually be rolled up into the product version of Telegraph, the open source available version, as soon as I can finish writing a pull request to get it done. Right? The interesting thing about Telegraph is that it's open source and it's got something like 180 or something plugins for it, and almost none of them are written by InfluxData employees, right? They're almost all contributed by the open source community, from companies or users who say, it really needs to collect this kind of data. So they write a plugin for that and they get a pull request and it ends up in Telegraph, which is how I'm getting plugins in there too. I needed this one, so I wrote it and I did a pull request and in it goes.
So I think we're running out of time
Okay.
here.
Thank you.
Thank you very much.